Okay, this is vector lesson number 2 for those of you that may have missed class or need some additional help. I'm going to go through 2 of the application problems, one being an airplane problem, the other being the force vector. And Mr. Fogg, who is not a special guest here, but should be, helped me to design or help me understand a little easier way we think to teach vectors. So let me go through this airplane problem with you, and then we will do the, oops, my pen. Then we'll do that pulley problem. Okay, so this problem reads that we have an airplane traveling at an airspeed of 860 kilometers per hour at 148 degrees from the north, clockwise from north. So I would like to be able to use the law of cosines for this, because if it's 148 clockwise from north, but the true course of the plane is 140, it makes more sense to just set this up as a right triangle. However, the issue with that is we end up struggling with figuring out our angle when it's down here and all we have are our components. We could use the law of cosines, though, for that if we wanted to. But then that's going to find the angle in here, the angle between the vectors, which won't give me the true course from the north, which is really what I'm looking for. So I'd rather break it into components of a vector. So what I think I'm doing, the we think path is 860 magnitude, because that is the velocity, 160 kilometers per hour, at an angle of 148 clockwise from the north. Now I'd prefer to have that on a trig circle so that I can use my calculator to calculate that. So I'm going to subtract 90 degrees from it. Subtract 90, that gives me 58. So it's actually 58 degrees from the x-axis. Now if I'm going the opposite direction, that's 302 degrees. So I'm going to put in here cosine of 302, sine 302. Now whatever my calculator spits out will be right as far as sines. Okay, actual path, 800 cosine of, now we got to do the same process mathematically. 90 from my 140 gives me an angle here of 50, but I want to come from the other direction, so 50 taken from 360 is 310. Now we're just going to plug those in the calculator, and that's going to give me 2 vectors here and here in component form. Now why is that important? The components of the vectors here, if combined, will give me the components of the wind. Okay. And actually we need to subtract them, because components are over and down. So if we take these 2 components, just my over here, and subtract the over for this one, that should give me this distance right here. So 860 times cosine 302 came out to be 455. And we're going to the right, so it makes sense that it's positive. Now 860 times the sine of 302 comes out to be a negative number, which I'm glad of, because if it didn't, I'd be worried, because on a coordinate plane, shouldn't this one be negative? Okay, my next calculation is 300 times the cosine of 300, 800 times the cosine of 310, excuse me. That's 514.23, and then 800 times the sine of 310 gives me negative 612.83. Now it's a question of figuring out what operation to do with these components to be able to get the wind. Okay? And if you think about it, it should make sense. If I have the horizontal component for the 860 vector, it's going to be shorter than the horizontal component for the 800 vector. So when I subtract these, my wind, I can draw this in, should be going in a positive direction, both over and up. So both of these should be positive. So I want to take my actual path, subtract the we think path to get the components of my result. So 514.23 minus 455.83 66.73. That gives me a wind in component form of 58.5 and, let's do this calculation, negative 612.83 minus negative 729.32. That gives me 116, which is the difference in the components for the actual path and the we think path vertically and horizontally. Now, very important fact here. This vector can be translated to here so that it's centered at 0, 0. Simply be translated. So now my over for this vector is 58. My up for this vector is 116. Let's use this to find an angle. Tangent inverse of opposite over adjacent should give me my theta. Now I wrote it as a regular tangent problem. I could have written it as a tan inverse problem, but we're going to use the inverse tan to find the angle. 116.49 divided by 58.5 gives me an angle of 63.33 degrees, but if we look at this diagram, we're coming from the east towards the north. Now, if I want the size of that vector, or the magnitude, I'm just going to use the Pythagorean theorem. 58.5 squared plus 116.49 squared, and then take the square root of that result. So it's got a magnitude, use Pythag, of 130.35. So this is going to be kilometers per hour at this angle. Now I hate that. That shouldn't be east-north. That doesn't make sense. So to convert it, we just subtract it from 90 so that it's coming from the north, going towards the east instead. So 26.67 degrees northeast. And we're done. All right, next slide. And this is special guest star Mr. Fa's work. And it makes so much more sense to me than what we tried to do in class. So we'll probably talk about this in class, but I just want to go through it one more time with those of you that were gone. So, first step, when you're given the diagram for 85, you know we're 10 inches and 20 inches from, these are my tension ropes, and this is the distance those are set from where those pulleys are situated. Now this distance has to be the same because it's attached to the end of this. Well, that's the distance from the top to the bottom, 24. So I first found theta 1 and theta 2, these two angles. And those are just two simple calculations, 67.4 and 50.2. This one's more severe than this one, which makes sense. Okay, so now the x components of the t1 vector and the t2 vector, the x components of those have to be equal because the weight's at equilibrium. Force this way is pushing at the same rate as the force this way. So those two are equal. So I just said, let's make this x and this x, so x1 and x2, those are equal to one another. Okay, the next step. The y components have to add to counterbalance the 5,000 pounds. So I have to add the first vector y to the second vector y, and those have to add up to be 500. Or 5,000, excuse me. So I just made y1 equal to y, so that y2 was just 5,000 minus y. Now we're all in terms of a single set of variables, x and y. And this is what Mr. Fa did that I thought made so much more sense. Now he just wrote a tangent equation for my force vectors. Not my original problem, but my force vectors. So here is my new equation, or my new diagram. We have x and x, those two are equal. We've got y1 and y2, which this one will make y and this one will make 5,000 minus y. So then the tangent of this theta, sorry, this guy over here, my fault. The tangent of this theta should be y over x. And that angle, again, was 67.4. The tangent of this theta, 50.2, should be equal to 5,000 minus y over x. And that's that equation right there. Now it's just some simple math. I took this times x, cross multiplied, equals to y. I took tangent of 50.2 times x equals 5,000 minus y. Solved this one for y because this one was solved for y, set them equal to one another, and solved it. Now this gives me the x in this equation. That's the tension pulling from the right and the left. Plugged it back into this equation for x, 2.402 times that 1387.89 to get my y. That's this vector right here, the pull down vector. Now remember, these aren't equal because this theta is only 67 over here and it's 50 over here. So my two tensions are different pulling down. Okay, the tension on the first side is 3,333. The tension on the second side is 1,666. So now, one more calculation using sine, because if I go back to that diagram one more time, we now have numbers we can put in here. We've got 1387 and 1387, and then on this side I have 3,300. Whoops, I have them on the wrong side. Sorry. This is 1,666, and the one on this side is the 3,333.72. Now I'm just going to use, well, if I want this vector for T1, I'm going to use sine or cosine. Sine would be this 3,333.72 over T1. We also could use cosine of 1387 over T1, and then just solve those trig equations. Now, I don't know if it was less steps. I don't necessarily think it was less steps, but I think it was a lot easier to understand. Okay, so that's the second video. This one's going to be posted as applications on the V drive. If you do have any questions, feel free to email or whatever you need, and we'll try to get you guys all set up and ready for the test on Friday. I'll get this thing posted, ready to go. Thanks.